All right. Thank you, everybody. Right. So my talk is going to be on this secure aggregation. Yeah, secure aggregation for federated learning, and this is something that I've been recently working on at Yale with Arthur, Zayo, and Babis, my host over there. Right. I'll just one slide just on who I am. I'm currently a postdoc at Yale. And previously, I finished my PhD at North Carolina State University with Alessandro Scafuro, and Satwik is also from NC State, is my old colleague. Yeah, and really my research interests are in anything to do with privacy, anonymity in real-world systems. And I'm also on the job market starting fall, so reach out if anyone's hiring. All right, so let's get to federated learning. And before that, I'll just give you, an outline of the talk, what I'm going to talk about today. So first, I'm going to spend a considerable amount of time on just federated learning and the secure aggregation problem in general. We'll go over what are the constraints of secure aggregation in the federated learning space. Then, some, common approaches or easy approaches to solve secure aggregation in the federated learning context. And finally, I'll talk about our approach, like how we solve this problem. So all right, so let's get started with what federated learning is. So federated learning is really just collaborative learning of a model in some sense. So there are models on your phones. For instance, the quick type feature of Apple, or even the Google Gboard, which suggests some new suggests a word for you when you're already typing something. Or even Siri has a model on its own, running on your phone. Even Microsoft uses, it does federated learning for healthcare data to do, collaborative learning on healthcare data. All right, so how does federated learning really work? How does this collaborative learning work? So the idea is that first you have a server that's going to send a global model to your device, okay? And there is a model existing on my device already. And you get this global model from a server. So the device is going to compute updates to this model locally. Okay, so there's no communication so far. All the updates are going to be computed locally, and then the device is going to send these updates to the server, and the server is going to collect all these updates from multiple devices and is going to update the global model. All right. So crucially, just note that the updates themselves are computed locally on the device. The training data, which is maybe the private data or the sensitive data, never leaves the device. So you only have the updates that are going to leave the device. All right. So this is how, just in one page, how federated learning works. But there is a small issue with this, which is that even with the updates, or even with the model itself, people have found ways to reverse engineer this and learn, extract the training data itself. So this, which might be sensitive information which is on your device, or even that healthcare data, for instance, right? So this is not great. So even if you're just sending just the updates, the idea is that you can still extract the training data somehow. Okay, so what do we want? We want to do federated learning, but keep the data private, right? So this, the naive approach of just doing federated learning with this collaborative learning is not going to work. So let's actually just take a look at what is the update, right? What is the global update that the server is going to do? Once these parties have sent their local inputs or these local updates, what does the server do? What is the global update? So it turns out, this is a little bit of an abstraction, but turns out the only thing you're going to do is just take an average of the inputs. So you can think of this as just computing the sum. So you only want to compute the sum, or compute the average in some sense. You only need the server to compute the sum with all these inputs. That's all you want to do. But at by ensuring that these inputs are still private, the inputs of the clients are not seen by the server. So this is basically the secure aggregation problem. So we can think of private federated learning as just doing an MPC for the summation function, where you want that the server is the only party to learn the output, and all the other parties don't receive any output in this MPC function. The server has no input, and all the clients have some input x1 to xn. Okay, so this is what we want to do. We want an MPC for this particular function, and the server has no input, and the client is only parties who have input. Yes?
Is this input like the client data, or is this like after you've evaluated the model, the little gradients that you're adding?
Right. So it is after, this is not the client private data, it is after, it's just the updates. Just the, so you do the, the parties do their, retraining or, updates locally, and these x1 to xn are just the local updates that you're sending. So it's not exactly training data.
But they are private data, right?
It is private, yeah. Right, exactly. So, So there are attacks which reveal, if I reveal xi, then there are attacks which will, which help you get back the training data. But now I want to do an MPC. So an MPC, if I had an MPC function for, if I had an MPC protocol for this function, then I'm guaranteed that these xi are going to stay private, that nobody is going to, that's the property, that's what MPC gives us, right? Input privacy is one of the properties that MPC can give us. All right, so, and please keep asking me questions, yeah?
Is there any worry that, so even if you know the updates, like the combined updates, that you could still extract individual information? Like even if you know what you know is this average.
Right.
Dimensions or something like that, can you still get something useful out of it?
Right. So I think there are some works which try this, but it's shown that if you have if n is sufficiently large enough, then you don't learn don't learn enough about an individual's private input. You will still learn collectively. You can still collectively learn something about the data. Which might be something that you want anyway, right?
So the server can choose which devices are used for this, right? So in principle, at least in some scenarios, the server could just say that I'm just going to take your data and that's all for NF1.
Right. No, great point. So, great point in the sense that the server could, if the server were the one selecting which clients to use, then of course this attack works. But typically, we assume, or at least you need at least a threshold number of parties to participate. The protocols that we'll show later on will somehow factor this issue, factor this problem into the protocol itself. That only if a sufficient number of parties participate can you really get an output. But even then, the question is that okay, what if the server is the one choosing clients, and the server can corrupt a certain number of clients? So here we make some assumptions and say okay, at least a threshold number of clients need to be honest in the participating set. And ways to sort of implement this might be that the server doesn't really get to pick the clients themselves, and that there is some common randomness which allows parties to see, okay, this is my time to do an update of sort. So we try to, I might not talk about that later on because the selection function is sort of orthogonal to how the construction works, but previous works also assume that okay, there is some selection function which chooses based on some common randomness somewhere, with this set of clients are going to participate in the current iteration of the federated learning protocol.
Okay, another question. So do these devices don't have any authenticated channels between each other, right?
These devices, right?
Yeah.
Yeah, great. So this is just just motivation, like exactly. So they in fact we cannot do this, which I'll tell you in a second.
And this might be the start of a conversation rather than a question, but is the only operation really addition? Because if it is, this might be a good candidate for homomorphic encryption rather than.
Great. Yeah, you're spoiling the next few slides. But exactly, yeah, it is a great candidate for homomorphic encryption, and that is exactly what we do, and some previous works have also used in a certain sense. But there are a few other constraints which I'm going to talk about in a minute. All right, so this is what we want to do. We want MPC for this function, right? One party gets the output, and the others don't, and only the server does not have an input. Everybody else has some input. All right, so now actually let's go to what are some of the naive approaches that we can use to achieve secure aggregation in this federated learning context. Then I'm going to talk about some of the constraints in the federated learning space, which don't allow the naive approach. Then I'll talk about two recent works, both to be presented at Crypto this year, which work on the exact same problem, and how we compare with those works. All right. So the threat model is that so it's mostly a malicious adversary, but in this talk I'm going to a malicious adversary who can corrupt the server and some subset of the clients. But I'll also present protocols with just a semi-honest adversary and then build on top of that to go to a malicious adversary. All right, and some clients may collude with the server as well, right? All right. So let's see the first attempt, which is the threshold encryption approach. So suppose we could have the clients run a DKG and compute a common public key for say a homomorphic encryption scheme, maybe a threshold homomorphic encryption scheme, and you need to sort of run a DKG to compute this public key. Then the idea would be that the clients just encrypt their inputs using this using the public key that they just computed, send it to the server. The server is going to just sum them using the homomorphic property of the encryption scheme, and send back the aggregated ciphertext to the the clients here. The clients can then compute can partially decrypt each of these ciphertexts, this ciphertext, and send it back to the server, who can then just aggregate these ciphertexts, right? Okay, so this is a simple, easy approach to solve the problem, but there are two issues here, and one of which is what Kim was talking about earlier, that there are no you can't really expect channels between devices. For instance, my phone and your phone need not be connected to run a DKG. So this is not a great idea. And the second issue here is that you see that the clients sort of need to stay online to interact with the server, right? They need to stay online and they need to wait until the server is going to send an aggregated ciphertext and then compute something and send it back to the server. So it might be the case that some clients drop off because these are our phones. We go into an area where there's no network, or we switch off a phone, and then it should not be the case that the aggregation is just not completed. We could say that if we have some kind of threshold assumption, we can afford like up to some small threshold number of parties to drop off. But even then it's not great that the clients need to stay online, right? So this is attempt number one, and it's okay. Like we can't do it. One thing that kills it is that we need to run this DKG. Okay, so what we want is that we want like a one-shot protocol in some sense, right? Like so there is yet another issue if we have a one-shot protocol, and this is typical of the non-interactive MPC world. So assume that we have some magic function. So suppose the clients in one shot speak to the server, and we have some function which lets the server take the ciphertext and decrypt it and compute the output. Okay. Now the issue is that the server can run this as many times as it wants, right? Because you're only going to speak once. You don't need to speak to the clients again. Maybe I can use this magic function to compute some other subset of the ciphertext, and this ends up letting the server learn maybe inputs of a single party, right? This is a residual leakage attack, which is actually common in the non-interactive MPC world, and we don't want to solve this problem. We want to solve this problem as well, even if we consider like this one-shot interactions. All right. Okay. So I'm just sort of building up what are the things that what are the common issues with these problems, and then I'll show you just list them, and then we'll try to solve them later on. Okay, a second attempt might be just to sort of distribute these servers. Say we have two servers, and we have our clients, and the idea might just be to secret share, right? Let's just secret share our inputs to these two servers. Then the servers can aggregate these shares and finally compute the sum. So this is one nice, easy way to maybe solve the problem. It's one shot, no residual leakage attack, but unfortunately we are relying on this collusion assumption now that okay, we have these two servers. If they belong to the same organization, who are these two servers? All right, so those were the two sort of naive approaches. Okay, so now I'm going to go talk about just what are these constraints, and I will just reiterate, what I just mentioned so far. So the first one is that I don't want any inter-client interaction. I want it to be one shot, right? I don't want any interaction between the client and the server. I want a single server. I don't want two servers in my protocol. And finally, I don't want my protocol to suffer from the residual leakage attack. All right, so these are the main constraints in our secure aggregation protocol that in the federated learning space that we want to solve. Okay, so any questions so far? Yeah.
Do you assume that like public keys for all the clients are sort of
In the
known in some sense? Like do the client, is there some?
so far in the naive attempt one, in the first attempt, I assume that the clients are going to run a DKG. And the second one, yeah, so we can assume that the servers are the only ones who publish some public key, and we are encrypting with respect to that key. But moving forward, your question is going to make sense. Yes, I do assume that there will be some PKI, and that parties have some source of, like, I haven't thought about that too much, and I just assume that yeah, we know some central source where public keys of the parties that are selected in a particular round, everybody knows. Like, okay, these parties are selected, I can maybe retrieve from somewhere the public keys for the corresponding parties.
So some like identity provider or something that's
Yeah,
that is
exactly.
trusted, but they're like off to the side, not part of this.
Right, not part of this. Yeah, not part of this, exactly. But yeah, great question. And I feel like, there might be challenges there given the key transparency issues that you were talking about. Yeah, that's true. Okay, so what is the approach? So how did the two crypto papers solve this problem? And in fact, they achieve most of the most of the constraints are addressed in the two crypto papers. So I'm just going to tell you, give you a brief overview of how they solve the problem. And the idea is actually to use a committee. So it's kind of a little bit of a cheating in some sense, in the sense that, okay, now I still want everything to be one shot, but I'm now going to use a committee. And even our work uses this committee. So what happens in this committee-based approach? Like, I mean, the typical protocol looks like this. Okay, the clients speak once, and they're done. So this is the one-shot idea. And then the server is going to send something to the committee, and the committee is going to send something back to the server, and then the protocol is done. Like, so I'll tell you how they do it in a second. Right, so the clients are in some sense one shot. And here again, we assume that the server is, say, static and malicious and can collude with up to some threshold number of the committee and of the clients. Okay, so this is the, I guess the design. Like, so you assume this committee, but who is this committee is the question, right? Like, how do you instantiate this committee? So now I'm going to talk about these two works. Willow and OPA both are at crypto this year. So the approach is that you end up using this set of decryptors. Like in Willow, what Willow does is they say, okay, we have certain decryptors. They don't really specify who these decryptors are. But so in their protocol, they required the decryptors to run a DKG and then compute a public key, okay? So in some sense, in my head, I think of this as being, part of the server itself, because this seems like a designated decryptor in some sense. Okay, so now really the protocol is very simple. Now if I have a committee that is going to generate a public key there, this idea is exactly like what we saw in attempt one, where the server is, the clients are now going to encrypt using that public key. The server is going to aggregate the ciphertext, send it to the committee. Committee computes partial decryptions, and then you aggregate the partial decryptions to get the final output. So this is really attempt one that I was talking about, except that now instead of talking back with these clients, you're doing it with a committee where the committee has run a DKG to compute a public key. Yes?
Do you have to worry about things like the ciphertext, or the plain text, or whatever, being out of the right range or something like that? Like some malicious clients who try to
Oh, yeah, malicious client?
submit that input.
No, yes, you're right. So there is a, in the problem, like with respect to the secure aggregation problem, for federated learning, yes, it's an issue. This input validation is a So they call it input validation, which is that you prove something about the input. So in this work, and maybe today's talk, you'll see it in my future work slide, where I want to sort of tackle exactly that problem as well, because it is important, right? Because you can mess up the global model update if you send some arbitrary information as a client.
So presumably each of the clients can send zero knowledge proofs that the input is put in.
Right. Yeah. So you want an efficient way to do it, like in some sense. But maybe not a full-blown snark, but maybe something simpler, depending on the scheme, right? This is just the overall idea. So Willow actually does something more. Like, I mean, the protocol itself is kind of cooler in the sense that they use, so they don't encrypt their inputs using the DKG generated public key. In fact, they encrypt keys. And they use, this key is a key for a key additive and homomorphic encryption scheme. And you can aggregate these keys, and then the server basically gets a key to sort of decrypt the final ciphertext. So not really important in the sense that the flow is sort of the same, but the protocol is kind of a little bit more involved. In the sense that now basically you want to encrypt sort of vectors and not just a single input. So these model updates are typically vectors. So the goal to do this key additive homomorphic encryption and encrypt it using that is so that they can reduce the size of the ciphertexts itself that are sent to just sort of your keys, like encrypting keys rather than encrypting the input vectors themselves. But don't worry about it, like we don't need to go into that right now. Okay, and one other thing is that, how do you handle a malicious server here? Their idea is to, make use of yet another entity called a verifier. That sort of, the server sends something to the verifier, and the verifier sends like a certificate back to the server, who sends this to the committee, and then the committee can verify that, oh, okay, this certificate proves that the server aggregated these ciphertexts correctly. And this is kind of important it's coming up in at least with our protocol. This was a challenge on how to solve this in an efficient way, because we don't like this verifier either, because that's yet another entity who is not part of just the aggregation protocol, right? Okay, so that was Willow. Now the other one's called OPA, which is I think one-shot private aggregation, which is also at Crypto this year. And here I put phones here instead of the server. Why? Because in their protocol you don't need to do the DKG. So what they say is that clients are picked in in a particular iteration, and the clients are split into people who provide inputs and people who devices that will help with the aggregation. So these are also clients. So which is much better than what Willow is doing in the sense that they now it's all devices, right? You don't need any DKG, you don't need any external verifier of sorts. And what is the idea here? The idea here is actually it's reminiscent of the approach 2. So what you're going to do is you're going to compute shares for each of the committee members, encrypt it under the corresponding committee members' keys, send these ciphertexts to the server, and then the committee is basically going to decrypt, aggregate those shares as we saw in that approach 2, send the aggregated share back to the server, and the server can just recombine these aggregated shares and compute the final output, which is again approach 2 with the committee. So rather than using 2 servers here, they're going to use these committee. They're using a committee which is basically just clients. So you don't need them to do any PKI between themselves, so which is much better. So now I'll tell you what. Okay, so before I go ahead, let me just tell you. Okay, they do something more again, as in Willow, and they use something called seed homomorphic PRGs to sort of mask their inputs. And this primitive is actually quite similar to the key additive homomorphic encryption that we saw in the previous work. And again, so the idea is the same, but you're now going to send a seed and then secret share the seed and send it to the committee. The committee is going to aggregate, you get a final seed, and that seed is used to unmask whatever was sent here. Again, not very important right now, just see that this is the overall approach that was used. All right.
Probably important because those are phones, and so they can't get huge amounts of data.
Yeah, right, exactly. So it's just but they still do get a lot of data in the sense that they're going to get O of okay. So actually, let me just go to the next slide. So this is sort of just an asymptotic comparison between those works and our work, right? So the one thing with Willow is that they need a DKG for those parties, so that's not that great. Whereas these our work and the other work at Crypto don't need any DKG. And where I guess the protocol that I'm going to describe next is going to shine is that you only need constant communication everywhere between client to server, server to committee. My solution is also in the committee model, and all communication is just constant size. And here, of course, the communication is not that great because server to committee, there might be you need to send all those shares to each of the committee members. And in the computation world, right, so the clients now might need to do a lot more computation when they are, I put two things here because there are two versions of a protocol. If the clients know which cohort they're going to be in, then they can do some pre-processing beforehand and then get like just constant communication. But otherwise, they might need to do as much they might need to do computation depending on the size of the cohort in that particular iteration. Whereas OPA only requires O of M, which is compute the secret shares for all those committee members. And here it's just constant work for the clients.
But of course, all these, like, when you think of concrete numbers, all of these are proportional to the gradient size, right?
Yes, yeah. I did not put the gradient size anywhere here. So I'm assuming it's all just one, like just normalize everything to one.
Do you have a sense of like what kinds of numbers are generally used? Like how many clients, what kind of committee size would be reasonable?
Mm-hmm.
I guess like number of clients is a totally generic question about federated learning.
Right. I again, it depends on the application, but and I did try to look this up, but and some of this information, like for instance, when Apple does it, it's not really public how many, but at least with the experiments that we did and previous works did, they assume like around the order of hundreds of clients in each iteration, and the committee size was also around that, like tens to hundreds. The range was in the tens and hundreds. That's it. Not like in the thousands. Yeah.
You don't necessarily need to get all the clients involved in every iteration. Pick like a random subset of clients for each.
Right.
Right.
In each iteration. Yeah. In each iteration. Correct. Exactly.
So so how is it possible that in your work the server to the committee communication is linear?
Server to committee.
Linear is just in the
Linear in just
size
the
of the grid.
right. Linear in the size of the vector. Yeah. The grid. Yeah. Exactly. So I'll show you next. Right. Yeah. So so we find a way to sort of make the ciphertext. Yeah. So the ciphertext is in some sense. So there are ciphertext from clients, and we somehow manage to aggregate them, and we only need to send the aggregated ciphertext to the committee members. So it's just a constant size ciphertext. Wait, that was your question? Yeah. Okay. Yeah. So even OPA sort of does that, right? Like they need to send. So this O of n is for the verifiers, and they also. So if you look at the attempt 1, I guess. So what we were doing was. One second, let me just bring that back. Right. So. Right. So here, this ciphertext that is sent between 3 to 4, between 3 and 4, the server is just aggregated the ciphertext and is only going to send one ciphertext to the committee. Yeah. Right. Okay. All right. So yeah. So now let's talk about our approach. So what did we do? How did we achieve those numbers in at least those complexities in the previous slide? All right, so I'm going to just introduce our primitives, and our first primitive is this recent work by Sanjam Garg et al. At last year's Crypto, which is this primitive called silent threshold encryption. And basically, this lets you do threshold encryption without the DKG. So parties don't need to run a DKG to compute a common public key. They just need to do their own key generation and generate some hints. And using these hints, you can generate a public key on the fly and use it to encrypt and use it to decrypt. I mean, there is a way to decrypt. So now I guess things are going to get a little bit more technical. I'm going to go over the construction in some more detail, right? Okay, so what do they do? So you don't even, there's no DKG. What the parties need to do is just generate BLS keys, okay? Which is basically a group element of the secret key. And all clients are just going to compute this public key and secret key. And now we're going to sort of witness encrypt using the aggregated public key, such that if I have a signature, a BLS signature that verifies under the public key, I can decrypt the corresponding ciphertext. Okay. So for instance, if the ciphertext is with this aggregated public key, there's a tag which I've not really talked about, but all these constructions will require some kind of tag just to know that, okay, so for this, we are encrypting with respect to a tag, for this particular set of public keys. It might be the iteration count or maybe even the global model in the federated learning space that we'll see later. To decrypt, what you need is that the clients just provide a BLS signature with respect to the same tag, and you can just combine these signatures and decrypt using the aggregated signature. Okay, so this is, I'll show you the construction also just on the next slide, but this is the main idea. So now, here you can see that you don't need to do any kind of DKG. So parties have just generated keys here. There's an aggregated public key, which is computed on the fly. You say, okay, I want all of these guys to participate right now. I take the aggregated public key, and I can encrypt. I'll show you what this encryption looks like in a bit. And just with BLS signatures, you're able to decrypt. And this is actually very similar to the Bonnet-Franklin identity-based encryption scheme. Okay, so how does this encryption scheme really work? So to encrypt a message M with respect to some tag and public key, the idea is, okay, so this is also kind of a little reminiscent of El Gamal. It looks like, so you have two ciphertexts. One is like G to the R, and then this is the R that is the mask, and M is the message over here. Okay, and in the Bonnet-Franklin IBE, this tag is actually the ID of the party itself. All right, and to decrypt, all you need to do is just compute CT2, which is this guy, minus the pairing of CT1 and the BLS signature. Okay, and just to see why it works, if I have E of CT1 sigma, that is just R, the group element R, and SK times hash of tag, which is what a BLS signature looks like. And if I just move things around a little bit, I get exactly what is computed here, right? So CT2 minus this guy will give the message M. Okay, so this is a witness encryption scheme where the witness is a BLS signature that lets you decrypt a message. And we also know that BLS signatures are aggregatable, like they're easy to aggregate, right? So in some sense, if I have an aggregated public key and I have 3 different signatures, I can aggregate those signatures, and I now have a signature on the same tag that verifies under the aggregated public key. Okay, so far so good. Okay, so this is the main, so this is the main idea in that silent threshold encryption scheme, but they so I didn't talk about threshold in this construction here, and I will not really talk about the threshold part of it. There are some complicated ways to add threshold to the protocol, but for now this is the general idea. So you're going to encrypt with respect to public key, and you can decrypt if you have a signature that verifies under this public key. Okay, so when encrypted under the same tag, the threshold encryption scheme is actually also homomorphic. Okay, so this is something that we just observe, that we can. It's quite easy to make the encryption scheme homomorphic. And just to see what it looks like, if I have this ciphertext is the homomorphically added ciphertext, which has the same shape as one of those the ciphertext that I showed you in the previous slide. All right. So that is the homomorphic STE. Okay. One other issue is that okay. So I told you that a BLS signature is used to decrypt, right? So now, say I'm given these three ciphertexts: a ciphertext encrypting M1, M2, and a third ciphertext encrypting M1 plus M2. And to decrypt, you basically need just a BLS signature on tag. It has nothing to do with the messages or the ciphertext itself. So it's not really bound to the ciphertext. So this signature really allows you to decrypt all the ciphertext, right? So this is sort of like a small issue that we need to fix, and the fix is not that challenging. We just need to change what the decryption looks like. So it's not a BLS signature anymore, but it's now bound to a ciphertext. Okay. So now, if I wanted to do decrypt, I would just do CT2 minus E of sigma and hash of tag. Previously, it was CT1 and the signature. But now sigma is now SK times CT1, and just to see that why it works, I can just, if I just expand this out, it shows up. It becomes the same thing that we were doing previously in the previous slide, whatever I showed you. All right, so cool. So there were two issues. I needed to make them homomorphic, and I need to sort of make it ciphertext bound. Right. So now let's just for a semi-honest adversary, the idea is sort of what Willow does in some sense, in the sense that now I don't need them to run a DKG, right? I just have these parties, and they have these keys are supposed to be different, right? So these are parties with their own keys, and now the idea is that the clients can, so they're all clients, like they're all devices. We just know that, okay, these are the parties selected in this round to serve as the committee. These are the parties that are going to give the input. So the clients can compute, the aggregated public key for all of these guys, compute ciphertext. So this would be the aggregated public key for all of these guys. The clients then encrypt with respect to that aggregated public key and a tag, send the ciphertext to the server. The server is going to aggregate those ciphertexts, send it to the committee. Committee computes those partial decryptions and allows the server to compute the aggregate. All right, so for a semi-honest adversary, this works. This is great. We can just, it's sort of, instead of using threshold encryption, I use now silent threshold encryption, which allows me to, sort of ensure that these parties can, they can be selected at random, or, once they're selected, they don't need to run a DKG. We can compute the aggregated public key for these guys on the fly. Okay, cool. So this was for semi-honest adversaries. So the next thing that we're going to talk about is a malicious server, right? So let's just first see what a malicious server can do. So the one thing, the first thing on observation that a malicious server can do is that, so now the committee does not really see the ciphertext, right? The committee gets ciphertext, it doesn't, how can it distinguish between, like, say, an individual ciphertext versus an aggregated ciphertext? For instance, the server could just send one of the honest party's ciphertext and have the server decrypt it, and then the server just immediately learns that particular party's input, right? And the server can also craft ciphertext on behalf of honest clients, because all the server is doing is, in some sense, forwarding these ciphertexts that it received. Sort of aggregating the ciphertext and sending it to the clients. The server can do this themselves. So one naive fix might be that, okay, we just have the clients sign their ciphertext. So they send signatures along with the ciphertext. The server can then forward all of the ciphertext and the signatures to the committee, and the committee is going to then verify the signatures, aggregate the ciphertext, and then compute the partial decryption and send it back. But this is not good. Why? Because the communication complexity is going to blow up, right? Like for each committee member, I need to send so many signatures and ciphertexts. And in fact, Willow sort of, when they use the verifier, this is where they also suffer a similar communication complexity because they need to send stuff to the verifier, and the verifier is going to aggregate stuff and send it back. Yes?
Did you think about using like differential privacy for this problem?
Oh, so there are some works that actually use differential privacy, and that's also a great solution. But yeah, we didn't. I don't know. We wanted like full accuracy, I guess, in some sense. These were like an MPC-based approach. But no. There are some works that have tried to do this with differential privacy. I think Apple has some work.
But that also rules out sort of the same attack, right? You could decrypt one ciphertext, but it wouldn't, if you add noise, and then it doesn't reveal anything about the particular user.
Right.
So that's sort of, this is the problem with the differential privacy.
Right. So wait. So you mean instead of oh right. Oh yeah. Yeah, right. So because if it's noisy, then but even then the server can just send that particular party's ciphertext and have the committee decrypt that.
So
but the noise.
If the committee adds the noise, then you can they can add enough noise
Okay.
that it would drown out a single user's.
Users in sure, right. Yeah, I guess that would also work, right? Okay, but I didn't think about that. But it's a good point.
You also get noisy results.
Right. Yeah, that's the trade-off, right? I guess.
As far as I understand, the most common approach, well, I'm not an expert in this, but I think the most common approach in DP is to use local, in Federated Learning is to use local DP, if any. So, yeah. I don't know if any global DP. Yeah, I don't know. So that could make sense, right?
Yeah, that could make sense. Yeah.
Community-based global DP.
That could actually make sense. Yeah.
Community-based.
Okay. Okay. Yeah, but there's a small trade-off of adding noise. Okay, so this is, I think, where something cooler, like a new cooler primitive that we sort of introduced, which is called a multi-key linearly homomorphic threshold signatures. So I'll just break that down. So what do I mean by multi-key linearly homomorphic signatures? So suppose I have two signatures, signing M1 and M2. I can somehow aggregate these signatures to get a signature on M1 plus M2 that is verifiable under the sum of the verification keys. Okay? So this is what I want to achieve. And if you think about it, if I have such a signature scheme, then I can get constant communication, right? I don't need to send all the signatures and all the ciphertexts. I can somehow aggregate the signatures, aggregate the ciphertext, and now I have an aggregated signature on the aggregated ciphertext that the committee can then verify, right? Yes.
Do you still, somebody still has to tell the committee which public keys went into this aggregation, right?
Yes. So I'm again. No, correct. In the sense that, so the committee already knows. So what I'm assuming here is that the selection is in some sense publicly known. So all parties know that, so there is some common randomness that all clients can just run, and they learn instantly that, okay, in this iteration, these are the set of parties that are going to participate. And I'm also maybe cheating a bit in the sense that I assume that the committee members then know which are the public keys of the parties that are going to participate in this current iteration. So they know the set of public keys themselves. I don't need but now when the threshold assumption comes in, of course, we don't know which public keys were used to aggregate, but we don't need that here. So we just need to know the overall set of public keys in that particular iteration. We don't need the server to send after aggregation the list of public keys that were used. So I'll show you how. Okay. So this, yes, you have a question?
So I'm a little concerned about the malleability. Because the usual definition of a signature, right, is that given a pile of signatures, you can't create any additional signature that wasn't in that pile.
Right.
And now you're able to generate signatures of things that were in the side. So I guess the definitions could be interesting.
Yeah, right. Yeah. I would have a slide on that, but I don't think I have that today. But we can talk about this for sure. Yeah. The definition too.
Is it sort of tag-based, or is there something hidden here that's like, means that these secret keys can't be mixed across?
Yeah, across different sessions. Correct. Yeah, there is a tag associated. In fact, I have like what my construction looks like. So it's a very simple signature. The signature is, and right now, this is just a placeholder, okay? So the signature is actually, it looks very close to the BLS signature, except that I'm also going to sign the message in such a way. So this is for a particular tag, and I'm going to do M to the SK. So that's the signature. And the verification, looks very similar to BLS, except that, we have this additional term of VKNM, which is just secret key and M. Okay. Okay. So this signature is verifiable in this way. But now I'm going to talk about some challenges that show up when I actually add these signatures, because this verification equation might not hold when signatures are aggregated, which I'm going to show you in the next slide. Okay. So just once more, multi-key linearly homomorphic basically means I can do linear operations on the messages, and even if they're signed under different keys. But they all need to be signed with respect to the same tag. Okay, so in just some more detail, so let's take two signatures which are of the same shape that I showed you in the previous slide. If I add them, I get secret key 1 plus secret key 2 hash of tag plus basically SK1 M1 plus SK2 M2, right? And I showed you in the previous slide that the verification would so this was the verification for a single signature. Now let's just see if it works for an aggregated signature, for the sum of two verification keys and the sum of two messages here. So the second term here, right, this is going to be a little problematic. When you look at it, if I just were to, so why does this show up? Because in the, right, so basically I'm opening up this half, okay? So I just took VK1 plus VK2, which is SK1 plus SK2 group element 1, moved it to this side. So I have SK1 plus SK2 times M1 plus M2. If I were to open it up, I have SK1 M1 plus SK2 M2, which is part of my original signature, which is good. But this second half has some cross terms, which are not great, right? Now, I cannot expect clients to know what somebody else's message is. So they cannot really compute this and send it anyway to the server. So this verification equation doesn't really work right now. Okay, so and the verifier really has only VK1 plus VK2, which is the aggregate of the verification keys, and maybe the aggregated ciphertext, which or the aggregated messages, which are M1 plus M2. Okay, so now how do we, so this verification equation does not work. Okay, so the trick is to use this generalized sum check algorithm, which is common in the Plonk kind of proof systems, and actually also used in another paper by Garg, which is HINTS, which is the silent threshold signatures protocol. And the idea is that if you have right, so if you have a polynomial, if you have polynomials ax, bx, you can write, there exists these polynomials qx and qz such that this equation satisfies. Okay. Now I would replace, so the goal is to somehow come up with a verification equation for the verifiers, okay, on the aggregated signature. So that's what I'm trying to build up. So now suppose I just replace a and b with sk and m. Just replacing things here, it's going to look like skx times mx is equal to ski mi plus some the polynomials q and z. And if I were to verify this polynomial using pairing checks, it looks like this. Okay, so I just pull it down here with some pairing checks, and this part is actually part of the aggregated signature. If you remember, we had SKI MI in the previous slide, right? And now what is missing is really the tag-based stuff. And the idea is that one thing that I did not mention is that how do you really compute these polynomials or polynomials in the exponent, they can actually be all computed with the hints that parties would send, or as part of the signature they can just send some extra group elements, which allows, so the clients are going to send these extra group elements which would allow the server to somehow compute all of these polynomials as well, which again I won't cover, which I won't talk about in the talk, but I'll just show you how the overall signature is verified. So this is the same pairing equation from the previous slide. All I'm going to do is add this hash of tag. So this is all public information. I'm just adding this to both sides of the pairing equation. And if you look at, if you use these two pairings and sort of combine them, what we get is in fact the final, the aggregated signature itself. Like, it's kind of maybe difficult to parse here, but the idea is that there is a way to make the verification equation work, all with public information and just the signature. So all these polynomials qx, qz that I did not really talk about, those can be computed by the server with some hints, and everything else like avk, which is the aggregated verification key, and the hash of the tag, and this polynomial of computed with the messages can also all be computed with some hints that the clients are going to send.
How big are the hints?
So each, no, great question. So the hints are still constant sized, but they're group elements, and there will be, I think, with the signature there are like 6 group elements that need to be sent. But there is some pre-processing that the server needs to do, which is order of the number of parties in the system. And this pre-processing that the server will need to do, I mean, so where do those n hints come from? Those would be generated at the beginning of time. So we assume that in a setup phase, the clients will have generated all these hints along with their keys, and then the server is going to collect like n of them, and they need to do some computation at that point to compute those hints in the pre-processing phase. But right now, as part of the signature, it's all just like, I think 6 or 7 group elements is all that need to be sent, which is part of the signature.
I guess how much bigger do the public keys need to get? Is that
How big are they?
the user for the client public keys? How much bigger do they get?
Uh,
'Cause you're saying basically you add a bunch of hint information.
oh yeah.
So that's
Yeah.
not the 6, that's
Right. Okay. So no. Yeah. So the client public keys in the beginning, they will be O of n. So there are n, or actually not even n. It might be something with respect to the universe. So they generate BLS keys plus I think so say n star group elements, where n star is the set of not the iteration but the whole universe. They need to send some group element and upload it there for the server to somehow use and aggregate.
Is that some like g to the secret to the power or something like
Yes,
that?
exactly. G to the secret to any Lagrange coefficients, which basically helps them compute this polynomial and these polynomials. So these polynomials are require right, exactly, all these terms which the clients help in the beginning of time. Yeah, but in the online interactive phase, I mean, or the online phase where they're going to send this, we only need fewer group elements, like it's constant sized, a constant number of group elements. Okay, so I guess I'm almost done, and I'm just going to tell you what the final protocol sort of looks like. So the idea is that the clients are going to encrypt their inputs using the silent threshold encryption scheme, and they're going to sign the ciphertext using the multi-key linearly homomorphic threshold signature scheme. Okay, they're going to send the ciphertext and signatures to the server. The server is going to aggregate the signatures, aggregate the ciphertext. So now it has a constant size signature, constant size ciphertext. Send it to the committee. The committee is going to verify the signature and send partial decryptions back to the server, and the server is going to use these partial decryptions, aggregate them, and compute the final sum. So the new idea, I think, is just coming up with this signature scheme, which lets you sort of aggregate these signatures and then compute a single signature, like a constant size signature, to the server. And as long as the threshold number of parties are participating, it's easy to aggregate. I mean, it's easy to compute a signature. I mean, not easy. I mean, like, I mean, it's possible to compute a signature, a verifiable signature. Right. So, I guess that's it. So just to conclude, right. So we sort of show a new way to solve the federated learning problem with just constant communication, a new primitive, multi-key linearly homomorphic threshold signatures. So multi-key homomorphic signatures do exist. Like there are constructions, and in fact there is a multi-key linearly homomorphic encryption scheme as well. And our construction is kind of inspired from that. The threshold is new, and the size of the signatures are also constant size, whereas previously they required sending more data. Okay, and just to end with some future work, right now my message space is actually in the exponent. So I really rely on the fact that in federated learning the updates are kind of small, so computing the discrete log is kind of easier, but there might be ways to sort of improve on that. And the second one is what we discussed earlier, which is the input validation problem, that we want somehow the clients to be able to prove that the inputs are in a particular range or whatever. Right? Yeah. So that's the end of my talk. Thank you.